All right. So today we're going to look at a few topics, pulse response, digital approximations, and stability. This is lecture 3. Last week, we started off with this difference equation. Okay, so if you look at this expression over here, you will see U and Y. U and Y. The U's are the inputs, Y's are the outputs, the response of the plant. I'm just giving you a little summary if you have forgotten certain things. This is a difference equation, okay? So the signals are time stamped. Say, for example, UK is the input at time K, right? And UK minus 1 is the input at time K minus 1. It's a different time, okay? And so on and so forth. So this is the sequence of input signals. The input signal now, input signal 1 step back, input signal 2 steps back, like that. The K represent the time stamp. So in discrete time, you can avoid that word time altogether and stick to index, time index. First sample, second sample, third, fourth, and so on. So the time in between two consecutive signals is called the sampling interval, right? And you can record it somewhere and just keep it there. You don't have to bring it into the equation, okay? You use sampling interval in the process, and at some point, you remove that from the equation and stick only to the index, K, okay? And on the left-hand side, you can see all the responses, right? If it is a single input, single output system, right, which is very easy to understand, the response Y changes from K to K plus 1, K plus 2, and so on, right? So this is that signal. So if you want to build the transfer function is the ratio between response and the input signal to the function, which is Y over U. Okay, so this is what you want to find out, Y over U. But in this format, you can't do that, okay? Because these are different times, different moments on time axis. So that is why we use Z transforms to get rid of this discrete nature, right? In the form of a wrapping around the discrete time, right? In order to get to something on a different domain, we call it Z domain. Now, if you see this one, when the transformation happens, right, Yk becomes Yz, and Yk minus 1 becomes Z to the minus 1 Yz. So you can see Yz being common with a little modifier here, Z to the minus 1, okay? So all the other delayed samples like Yk minus n, for example, it looks like Z to the minus n Yz. Okay, so this Z to the power minus n means how many steps the sample is delayed. Okay, and the beauty of this transformation is that now you can take Yz as a common element, and all the other multipliers or coefficients can be grouped together as a one big coefficient of in front of Yz. Same thing happens on the right hand side. Then you can easily get Yz over Uz and call it the transfer function. Okay. So when you see this rational polynomial of Z to the minus powers, right, you should be able to understand that it has come from something like this, and it is a difference equation, okay, in discrete time. So after that, I think 2 weeks back, we drew this structure. Sometimes it's easier to see things rather than read things, okay? So when you see things, you understand much more than what you really understand from an equation like this, how things are connected and so on. And this structure is also important for you to figure out if you want to really implement this controller on real programmable electronics like microcontrollers or SBCs, right? This is your program, how you add things together, how you multiply things together, whatever, right? Okay. And how you manage the data in the memory and how you shift the data on your registers as you step up from K to K plus 1 to K plus 2 and so on. Right. So I think we worked out this example also, right? Uh, just to get you a bit more practice. So if you look at this one, is it transfer function? Now it is already given, okay? There is another way of modeling. We call it state space model, right? So there you can see transfer function to state space model. Now the difference is this. Transfer function can be higher order, any order, depending on the complexity of the function. Okay, sometimes you have seen second order transfer functions, third, fourth, fifth, like that. So transfer function order can be a problem at certain situations, right? You want to break it down into a number of lower order systems, okay, at least for modeling. That's why the state space model is there. So what the state space model is doing is that it takes the higher order system, let's say fifth order system, and breaks it down to 5 first order systems, right? So solving the first order system is very, very easy, right? And you can solve 5 of them quite efficiently than trying to solve the fifth order one straight away. Okay, that is the whole purpose. Now, this example illustrates how you can do that. In control system context, we call it transferring the state space, the transfer function into state space model. So this is how we do that. Let's say we start with the transfer function here and you cross multiply and get into the Z transformation, right? And then take the inverse of that, right? And then you are here, the difference equation, the original difference equation. And for most of you, right, this is the origin. You start off with the difference equation, this one. And then you can go upwards to the transfer function or downwards to the state space model. Okay. But as you know, sometimes you are given the states, the transfer function, and you are asked to create the state space model. Or sometimes you are given the state space model and you are asked to get the transfer function. Okay. So either way, you have to go through the difference equation, this one. You can see it over here. K. K means the time index. Okay. So the way to get to the difference equation from the transfer function is cross multiplication and rearrangement of the equation. Now you can see here is a second order system. Then you have this difference equation. Yk is equal to minus 2 times yk minus 1 minus 3 times yk minus 2 plus 2 times uk. The input and the two previous outputs and the multipliers minus 2 minus 3. So creates the present response output, right? So this is how signals are related in the system. So if you have this driving signal UK, this is changing by its own, UK, right? You generate UK, right? Arbitrarily or through a certain criterion. If you have a controller will tell what UK is. And these are the two previous signals already there. And then you have this equation to tell what is the next outcome is. Okay. All right, so it goes on and on and on recursively. Now, if you don't like to work like this is what you could do. Figure out the most recent response, that is yk minus 1, and assign this one, okay, name it like x1. X1 is a state variable, okay. You're going to have two state variables for this one because it's a second order system. So two state variables. This is the first one. And then you figure out what is the next most recent uh, response signal, that is yk minus 2, right? Two steps away. So you call it x2. Okay, the most recent one is one step away, right? K minus 1 is given x1. And the other one is two steps away is given x2. Now from now on, we don't have y, okay? So we call the most recent one, okay, x1, or the signal two steps back as x2. And we call them on the same time k. This is also k, this is also k. Now all the signals on the right hand side are converted to time k, same time. Okay. So you're getting actually signals from the past and give it a new label like x2, right? And say it's present time. It's like you have seen like expired stuff rewrapped and put it to the market with a different brand and all, right? Something like that. State variables, right? And they're all samples, but you give a new look, x2, x3, and so on. Okay. Present time, like fresh variables. You do this except for one on the left-hand side, yk. The present signal, or the newest signal of the response, right? It's not given a state variable, right? Instead, what you do is you get the most recent one, k minus 1, okay? And the state variable given to that, which is x1k, you use that one to replace yk by stepping up this k to k plus 1, because you know that when k changes to k plus 1, which means you're going forward one step, in that case, yk minus 1 is yk. All right. So therefore, you can say the same thing over here. x1k goes to x1k plus 1. All right. So that's what happens there. And then you look at the other relationships over here, right? This variable, when the time steps up, right, it becomes yk plus 1. So therefore, the signal which is over here, x2k, right, in the next moment, it will be x2k plus 1, which is actually yk minus 1, right? And it is already given a variable x1k. So these two are equal. You can call it either x1k or x2k plus 1. Okay, so it's the same variable written using two state variables. One is at time k, the other one is at time k plus 1. So you can see these two arrows, they are two equations here. This is a second order system. It has two state variables. It has two state equations. So these bent arrows are the state equations, like x2k plus 1 is equal to x1k is equal to x2k plus 1. Here, this one, okay? You can see it over here. x2k plus 1 is equal to x1k, these two. And also, you can say x1k plus 1, which is over here, which is yk, is equal to this whole thing. This is x1k, this is x2k, right? You are replacing this system equation using the state variables already assigned, right? So you get the first state equation and the second state equation. And after that, what you do is you put it into the matrix format, right? They are all k plus 1, time k plus 1. And they are all time k, right? And x and k are two different signals. So you assemble x signals using this coefficient matrix, system matrix. This matrix explains how the variables are connected to each other, plus the input signal uk. All right. And you can see there are two equations here. UK appears only in the first equation. So therefore, UK contribution in the second equation is nil. So we have 0 here. Okay. When you write down a system, right, in the form of this equation, where you can see the rate of change of state variables, and here the values of the state variables, and there's some connection matrix over here, plus some constant times input signal, right? This is what is called the control affine form of the transfer function or state space model or just model, right? Canonical form or control affine form. This is the most important form that you need to write your model in, right, for almost everything, analysis, controller design, etc. Right. So together with the state space model, a part of that is the output equation, which is, if you look at the system, your output is yk, right? Now, yk has this equation. There's no point of writing this again. But what we do is that now we have state variables, x1k, x2k, and so on. So if you look at the second equation over here, right? Sorry, this one over here, yk, right, is equal to x1, k plus 1. So all what you need to do is that take your x1, right, and evaluate at k plus 1. So that is yk. Okay. Now, if you followed this process in an abstract manner in the sense that without attaching too much into any of these things, and if you followed this in a very generic manner so that you understand the principles, right, you will see that you can apply this for almost any system, okay, and figure out all what you need is this difference equation. And after that, you can apply this process to the difference equation and get the state space model very easily. Okay, right. I think I can skip this one because I've already explained it. Only difference here and the one before that is that this goes up to minus n, is it to the minus n. So this is the nth order one, whereas the previous one is second order, right? I started with this simple second order thing so that you can understand the process quite easily. But you need to actually be able to understand this for an nth order plan, something like this. Okay. In that case, there are so many state variables, actually n number of state variables. And this is x1, this is x2, this is xn minus 1, this is xn, right? N number of state variables. But doesn't matter. Eventually, they all will be packaged into this format. You have x1, x2, x3, x4, up to xn over here, n state variables. And on the left-hand side here, you have their next values, right? x1k plus 1, x2k plus 1, like that, x3k plus 1. All of these x1 to xn state variables, their values at time k, their values at time k plus 1. Okay, so that is what the state space model is in discrete time. Okay. And depending on what you want to measure as your output, you need to write down this equation manually. If it's a single input, single output system, it's just one output, yk. If it is a multi-output system, then you have many signals over here. And in that case, this will also become like matrix equation. Okay, right. For nth order system, your state equations will look like this. Okay. If you look at the given difference equation, it will form into this format, x1k plus 1, and over here, the first one is x1k, then the next one is x2k, last one is xnk, and their coefficients are a1, a2, up to an, all negative, okay? Plus uk, that is the input signal. And in addition to that, you have other state equations for each and every state variable starting x2, right? K plus 1 is equal to x1k, and x3k plus 1 is equal to x2k. All right, it goes like that. Then you can package it into this format, very generic format. This is the canonical form, or the control affine format, where the state variables and input signals are separated with this plus sign over here, right? And this is the values of the state variables the next moment of time. Okay. Now, if you look at this one, we will do the continuous time state space model, right? Maybe a little later. In that case, you will see pretty much the same thing, but there's no k or k plus 1. There's no such thing. It is basically t, x1t, x2t, up to xnt. All right. And here, can anybody suggest what will come over here, replacing x1k plus 1, x2k plus 1, and so on in the continuous time? Can anybody guess? Anyone? Oh, we have some activities in the chat. X dot, x double dot, derivatives of x. Okay, I think the first answer is correct. X dot. X dot. It doesn't go beyond the first derivative, because then there's no purpose, right? Because the whole purpose of having the state space model is to reduce it into the first order. Reduce it into the first order. So in the discrete time, the first order means k to k plus 1. K to k plus 1. So these are all first order difference equations. This one, this one, this one, or these ones, right? First order difference equations. K to k plus 1. And the continuous time, it is t to the dot t, right? x1 dot t. Here it is x1t. Here it is x2 dot t. Here it is x2t, right? Rate of change over here, the present value over here. Okay, all right, good. We also looked at the pulse response last week briefly, no, 2 weeks back. In the continuous time, we usually do the step response, right? Single input, single step rather. So like this. But in discrete time, there's no such continuity. So it's just a impulse like this. Okay. So this is continuous time. This is discrete time. So here, what you see is a discrete transfer function, Pz. Let's say it is a first order one, right? To start with something simple. Uh, and we know that unit pulse response means input is a unit pulse, right? This height is 1 actually. So if you look at the time definition of UK, unit uh, uh, unit pulse case is actually uh, the definition k from 0 to infinity, right? Whatever function you are given, discrete function, is it to the minus k. So that is the Z transform definition. And if you put that one into here, that just single impulse, right? There is something only at time 0, and it is just 1. There's nothing before or after that, right? So therefore, only the first sample u0 times z to the minus 0 is there. You don't have to worry about anything else, and it is, of course, 1. All right. So the unit pulse in discrete time is 1. And you calculate your y z, the response, using this equation, p z u z. You have p z, you have u z, and u z is 1. So it becomes simply p z. And if you want to get yk, that is the response, it is the inverse Z transform of p z. So this is pretty straightforward. And the analogous expression for what you have seen in continuous time, right? As a sentence, we can say it like this: pulse response of a system is the inverse Z transform of the system transfer function. Remember, we did the same thing in continuous time, inverse Laplace, right? Of a transfer function in continuous time, right, is the unit step response. Remember that? Unit impulse response. So here we see the same thing, but instead of inverse Laplace, we have inverse Z transform. Okay. Right. So when you evaluate this one, you will see a series of impulses, right, depending on the given transfer function. Right. Now it's time to look at another example. Let's say Pz is equal to B1 Z over Z minus A1, right? So this is a first order system uh, with a single pole at Z equals A1, right? So the pulse response, unit pulse response is, as we have seen earlier in the previous slide, is the inverse Z transform of Pz. So inverse Z of B1 Z over Z minus A1. So B1 is a constant. Then it becomes Z over Z minus A1 and the inverse Z transform. So if you look at the table, Z transform table, you will see this entry in there, that the Z transform of A to the K exponential function, K is the time index, is equal to Z over Z minus A, right? You take this K out and bring the value, the coefficient A, into this format, Z over Z minus A. So this is the Z transform, right? This is a very common entry in the Z transform table, right? So the moment you see this one, the inverse Z is this constant, whatever it is, this has to be minus, of course, right? The constant raised to the power of K. K is the time index, discrete time. And in front of that, you have B1. anyway as a gain. Now, when you put this k here, k is of course 0, 1, 2, 3, 4, 5, like that. Okay. It's not going to change. It's a constant sequence, starting from 0 and ticking 1, 2, 3, 4, like that. Now, this discrete system, right, always has sampling process. You know that, right? Usually the discrete systems come from continuous time, let's say, right? But I want to mention you something here. When we study control systems, we predominantly or very often say this, that the systems are continuous and we discretize it, right? In engineering, that is what we do. But if you go into the physics side, quantum mechanics and so on, they say the nature is discrete, and when you combine these things together, it becomes continuous. All right. So therefore, do not get confused of any of these things, right? Engineering is an applied science. It's not pure science, right? It's how we do designs and all, how do we control things, etc. And the famous thing is that Newton's laws, we use it quite often. And we know that it is not a pure representation of the nature, right? Whereas if you look at Einstein's theories, which is very close to the actual world, by far the best explanation of the space and time and energy and everything, right? But it doesn't mean Newton is wrong, right? There's no reason to say that, because all the observations, all the equations, the relationships, it explains, right? Whether it is pure, absolute way or not is a separate, different matter. Right. So having said that, let's get back to the main discussion. In control systems, right, we don't think like physicists, we think like technologists or engineers, right? There, we don't really look at the real world, how the world works in the quantum world and all that, right? So it's basically the gross world, the coarse world, the big world, right? Not the small atomic level interactions that we deal with here, right? So my point is this k being 0, 1, 2, 3, 4, 5. It doesn't change, right? And of course, you know, at some point, this system has gone through a sampling process before you get over here. You know that, right? But if you just look at this one, you don't see any sampling information here, sampling interval or sampling frequency. What happened to that? We don't know, right? Actually, the sampling thing is already included here in this A, right? This A is not only the system, it is system plus sampling together, right? So what you need to understand here is that when you have a plant, you can have an infinite number of discrete time models from the same system. Say you have one machine, you can discretize it using different sampling intervals and get different discrete models. So the discrete model of a plant is not only the plant itself, but sampling also together with it, right? Not only sampling, but there can be other things also. Everything put together is your discrete model. Remember that. A lot of people think the other way. Like if you have a system, when you discretize, you have a unique model, right? It's not very correct to understand it that way. you don't get a unique model in the discrete time when you discretize a continuous plant, right? Your model in a discrete time very much depends on the sampling interval you chose, right? Or any other modification that you introduced in the process, right? So therefore, this A1 is not only the original continuous plant, but discrete time, sampling interval, and other things, whatever in the process. I've already gone into this A. So remember it that way, all right? So therefore, once you discretize it using different sampling intervals, you eventually get to different A's, right? And K is unchanged. K is 0, 1, 2, 3, and so on. Right, okay. Now, B1, A1 to the power K is your signal, right? Pulse response is a signal. Now, B1 is a constant, right? We have no big issue with that one. But we have a little concern about A1, because when you raise A1 to the power K, right? K being like integers, 0, 1, 2, 3, and so on, right? This signal will exponentially decay. It will go down, reduce the intensity if the modulus of A1 is less than 1. You know that, right? If A1 is greater than 1, right? If this is greater than 1, when you raise it to the power K, it will increase, it will rise, okay? It will grow exponentially. So we call it unstable system. And not only that, if A1 is positive, if is a positive number, the signal Yk will always be positive. Okay. But if A1 is negative, when you raise it to the positive powers or even powers, it will be a positive value. But when you raise it to the odd powers like 1, 3, 5, 7, and so on, Yk will be negative. So every other signal will be negative. So you have positive, negative, positive, negative, so which means an oscillation. Then you will see an oscillation. Okay. So it's very important what the nature of A1 is in this particular case. So if I put that into a table like this, A1, right? This is the magnitude. This is the sign, right? So all these four cases, I can put it like this. If it is positive and greater than 1, right? Positive A1 and magnitude greater than 1. It is non-oscillatory, it's not oscillating, it is growing, gradually growing, exponential rise, it's unstable. And if it is less than 1 and positive, it's again non-oscillatory, it's not oscillating, but decaying. Then it is stable. And for the negative case, if it is greater than 1, it is oscillating, right? Oscillating and growing. It's oscillatory unstable. And the other one is oscillatory stable case. So now we understand that there is a zone on the Z plane, right? Which is connecting all these radius 1 points. Radius 1 points. So magnitude 1 means is a complex number. Magnitude is 1. So it is this circle. We call it unit circle. If you are inside the unit circle, you are stable. If you are outside the unit circle, you are unstable. So you can be stable in oscillatory manner or non-oscillatory manner. You can be unstable in oscillatory manner or non-oscillatory manner. Either way, right? So this is something you need to know about discrete time and Z plane, right? So if you compare the same thing you studied in semester 1 for continuous time, what we said was the negative half plane of S, right, is stable and positive part is unstable. Now, when you transform the continuous time into discrete time, right, with this is a transformation, the explanations change with the transformation. Now it is Z plane, and for stable cases, right, the poles are within the unit circle. And if the poles are outside the unit circle, the plant is unstable. So this is a mapping from continuous time to discrete time. The entire negative plane, negative half plane is mapped on negative half plane of negative half S plane is mapped onto what? The unit circle in the Z plane. Okay. So that's what essentially is happening here. Any questions? The best and most accurate way to understand this is that to think this discretization as a mapping from continuous time to discrete time. It's a mapping S to Z. So entire negative half plane in Z S is actually inside the unit circle of Z plane. Right. Now let's look at a second order system. Right now we have two poles. When you have two poles in the Z domain, the denominator becomes quadratic. Right, this is a denominator polynomial. Let's put a numerator polynomial also as nz. Okay. Now, in an abstract manner, I can explain the transfer function in this way. You can break this into two partial fractions, and it becomes q over z minus p plus q star over z minus p star, where when you break this down into two partial fractions, they become a pair of conjugate poles. Okay, right. So because I'm not really interested in pure real poles, because it is pretty much more of the same kind of thing, because here you have already worked out that for a real thing. Okay, even if it is a complex thing, it doesn't matter, but what's most obvious is the real case. So you can have two of these and still the same result. So therefore here I want to break it down into two partial fractions with more aligned with the pair of conjugate poles, right? So when you do that, the numerators also will become complex conjugate pair, right? So this is q here, this is q star here. So let's say I can write it down in a algebraic form, alpha plus j beta, right? And this is alpha minus j beta, and this p is in a radio coordinate form, r e to the j theta, and this one r e to the minus j theta. All right, and here you can see p and q. So you can see q and q star in algebraic form, alpha and beta. Alpha is real, beta is the imaginary part. And here for p and p star is a radio coordinate format, r e to the theta, right? J theta is minus j theta. So r and theta, this is r and this is the angle theta. Right. Now, now if you put the unit pulse over here as the input, you get the output. So we want to get to the output YZ. YZ is inverse of PZ. Now we bring in PZ, which is this one, right? You have to remember this one, right? Z times, this is the format we write it, okay? To make life easy, we take one Z out of the numerator. I think you saw that earlier also. We put this whole thing into this equation here, inverse Z transform of PZ. So this is that. So alpha plus j beta is a common factor. For this one, you can take it out. Not actually the common factor. You can take this one out for the first part, first term. Z to the minus 1, Z over Z minus RE to the j theta. And similarly, second term can be written like this. And now inverse Z transform, again, this is pretty common entry in the Z table, Z transform table, Z over Z minus something. And here also Z over Z minus something. So when you see that one, you know that in the time domain, it is this quantity, whatever it is, raised to the power k. Simple. So you take Re to the j theta as a one block and raise it to the power of k over here. And here is also the same. You take Re to the minus j theta, this whole thing, and raise it to the power k. All right. So after that, what you do is you see e to the j k theta, right? And here also e to the j k theta negative. So positive and negative terms, you combine together all the real terms, right? You have two terms here, and you have two real terms with alpha and two imaginary terms, right, with j. So if you separate out real and the imaginary terms together, you can write this equation. The first part over here with the two terms here, they are both real, and these ones are imaginary. That is why all these j terms are here. Okay. And it is very interesting to see here that e to the j k theta plus e to the minus j k theta, right? So you can write this as cosine. And this j, e to the j k theta minus e to the minus j k theta can be written as sine. So this is the trigonometric terms, okay? Then 2 comes over here, 2r to the k. This is alpha cos k theta minus beta sine k theta. All right. So now the cosine signals are anyway stable, right? They are going up and down, up and down. That's okay. And alpha is a constant, beta is also constant, right? This is the phase shifted sinusoidal waveform actually, right? You know, you can rewrite this one as, say, for example, sine A cos B minus cos A sine B, which is sine A minus B, okay? Is one single sinusoidal waveform with a phase shift, Whereas here, this cos k theta doesn't have a phase shift. Neither sine k theta has a phase shift. But because of the formatting here, when you write this down as sine A minus B, right, with a phase shift, okay? So this whole thing is a sinusoidal waveform, which is oscillatory and stable, but the signal can be even unstable based on the quantity over here, because this is a constant R being raised to the power k. So as k goes 1, 2, 3, 4, 5 like that, if R is more than 1, the whole signal is growing like in oscillatory manner. So therefore, for the signal to be stable, R has to be within the unit circle. So if it is inside the unit circle, it's stable. If it's outside the unit circle, it is unstable. So pretty obvious now, for discrete time system to be stable, the poles, all of them, they have to be within the unit circle. Okay. Any questions, please? All right. Is everything clear to everybody? So let me ask Mahendratna, is everything clear to you?
Yes, sir.
Okay.
Okay. Yeah.
All right. Vijay Tilaka, is everything clear? Then Vithanasiri, have you understood what we have discussed so far? Vithanasiri? Vihangi, what about you?
Yeah, yes.
Okay. Taraka?
Yes, sir. Understood.
Okay. Hevavasan?
Yes, sir.
Okay, good. Dhananjay?
Yes, I got it clear, sir.
All right. Then Chaturanga? All right. So let's move on then. And I want you to do this yourself, right? So I have not actually gone through step by step. I expect you to do that yourself, right? All these things, right? How the cosines and sines are written using the radio coordinate form of the complex numbers, right? So remember this one, Z is equal to R e to the plus or minus j theta, right? These are the system poles. So you can write down this as say cosine theta is equal to e to the j theta plus e to the minus j theta divided by 2, right? And you can write sine theta is equal to e to the j theta minus e to the j theta, right? Divided by 2j, right? So these are the trigonometric functions, right? So combining these things, you can replace the j terms here using sine. If you see something like this, right? And also you can say e to the j theta, say k theta or without k, right? Anything e to the j anything plus e to the minus j anything, right? This is equal to 2 cos k theta, 2 cos k theta. And this is equal to uh, sine k theta, and there is a j here, right? So this j and this j, there are two j's here, and they become -1. So please do this derivation yourself at home, right? Okay, so I have got some responses on the chat for those who are whose microphones are not working properly. All right. Now, next thing for us to discuss is obviously look into more details about this the waveforms and the poles. Okay, in the continuous time we have done it quite a bit. So what about in discrete time? We know that inside the unit circle the plant is stable, the response is stable. Okay, and if you pick up a point over here, right, you have a distance to the origin, we call it pole radius. So if I have my pole over here, the distance to the origin is the radius, right? And what is the importance of this radius? If I have a pole very close to the origin, what do I see? And if I have a pole farther away at the edge of the unit circle, what would it be, right, in terms of response? I want to analyze this as one of the first things, right? Okay. So if we pedal back to something we have already derived, where is that? All right. So let's stick to the second order plant over here, which is 2r to the k, okay, times the sinusoidal waveform. So this whole thing, as I explained, is nothing but a sinusoidal waveform with or without a phase shift, okay? Now, in front of that is the magnitude of the sinusoidal waveform. So most important thing is this whole thing, 2r to the k, okay? So the magnitude or the amplitude of the sinusoidal waveform, the response is 2r to the k. So can I give this to you? Little exercise, right? Determine the number of samples for the response to decay down to 1% of the initial magnitude. So I would rather call this amplitude, right? How many samples are required for the system to decay down to 1% of the original amplitude, right? Take a few minutes, maybe 3 minutes max, right? And try to figure that out. You have the equation, response magnitude or amplitude is 2r to the k. Using that one, calculate the number of samples the response is required to take the amplitude down to 1% of the original amplitude. Okay? Give it a try. All right. So, so this is the result. The amplitude of the response is 2r to the k. So, if you look at the amplitude at k equals 0, the first sample, right? It is 2r to the 0, which is just 2. Now, magnitude at k equals n after n samples, right? Or the nth sample is 2r to the n. So now you get the ratio, right? The amplitude at time equals n over amplitude at time equals 0, right? This one, which is r to the n, which is r to the n. And what we want to calculate is number of samples that is required until the amplitude drops to 0.01, 1%, right? So you get to this equation, and then you get the log, and this is your n. And after that, if you substitute for different r, so you know that the number of samples until the amplitude drops to 1% depends on the pole radius r, pole radius. So if you start off with something very close to the unit circle, right? Very close to the unit circle, say 0.9, you need about 43 samples. 43. After 43 samples only, it 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 is restricted plus or minus 1% of the original amplitude. If it is 0.8, that is the radius 0.8, somewhat we are moving inward towards the origin, okay? Then it is 21 samples. For radius 0.6, it is 9 samples. For radius 0.4, it is 5 samples, like that. So when you are very close to the unit circle, right, you have very slow decay, very slow decay. So need so many samples, right, to get the amplitude decay to a certain value. Whereas you are very close to the origin, your decay is very fast. Your decay is very fast, and you quickly get down to nearly zero. So this is something you better remember, okay, to interpret the response based on the pole locations, right? When the poles are near the origin and also inside near the unit circle and inside the unit circle, it's a slow decaying response, whereas if the poles are closer to the origin, right, it's a fast decaying system. Now, let's talk about pole angle and oscillation. Now, we know one thing, then let's take the other one, angle. Sometimes you can see the poles like this, right? Here, 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 like that. So pole angle is the angle that the pole creates with the real axis, you know, the complex plane. This is a complex plane, the angle. What if you have a small angle? What if you have a big angle, right? So this is in fact the sampling angle. So the angle between samples, in other words. Now, if you look at a cosine sinusoidal waveform, right, it's periodic. So every 2 pi, right, you get to the same value. So you can write down cos theta k is equal to cos theta k plus n, right? After n samples, right, you have the same value on either side. This happens when theta n, right, this is theta k times theta n, right, theta n equals 2 pi. After n samples, right, after n samples, you come to the same the value in the sinusoidal waveform. If you forget about the decay, right, let's forget about the decay now. Just look at the sinusoidal waveform. Then you can say n, number of samples, is 2 pi over theta. The moment you know this theta, you know how many samples in one cycle. How many samples in one cycle. So if theta is small, right, if theta is small, then you have so many more samples per period. And if theta is big, less samples per period. Now, you know certain things about discrete systems. And you know that you have heard about sampling theorem probably in your previous degree programs, right? How fast you get samples from a signal is very important. When you get more and more samples from the waveform, samples very closer to each other, you are capturing the signal. You are reading the signal very accurately. So in that case, your angle is very small like that, right? And the second one over here, which is something like, say, 70 degrees, right? You have big angle from one sample to the other one, next one, right? So then you are getting sparse data. You are not actually reading the waveform very closely. And if you have your pole somewhere over here, which means the angle is 180 degrees, which means for the sinusoidal waveform, you are taking one sample over here, the next one you are taking after 180 degrees. Okay, after the signal has gone down somewhere over here by 180 degrees. So you have lost entire waveform from here to here, but you are taking only one sample over here. Your samples will not represent the original waveform because much of the information has already gone unnoticed. You have not read those curves and variations. So your waveform is not useful. Your discrete samples do not represent the original waveform. So if you get a pole somewhere over here, that is your conclusion. But if you get poles over here, positive half plane, right, within the unit circle, then you can safely say, okay, my poles will represent not only the stability, but you also guarantee accuracy of the waveforms. Okay, so you can have a stable system, but not correct. Stability is one thing, accuracy is yet another one. Okay, so please understand that one. Now, if you have poles over here, for example, negative half plane, okay, so your sampling angle is too big. Sampling angle is too big. So when we say sampling, sometimes we refer to the sampling interval or sampling angle. Okay. Sampling interval is in time domain. You know the time in between two consecutive samples, right? But that is not really meaningful because you don't know how much the signal is changing during that interval. So therefore, much more meaningful information is sampling angle. So by the time you take the next sample, by what angle the waveform has changed. If it is too much, if it is like 70, 80 degrees, right, maybe you are marginally okay. But if it is 120, 130, 180 degrees, is simply useless information you are taking, right? Okay. Right. So let us take a little break over here, right? About 5 to 10 minutes, and we'll resume after that break. All right, welcome back. So let's look at how the sampling thing works. Right. So, so as I explained, this is the continuous time plant, right? So it is 1 over s plus a continuous time. And then you put a sampler, right, immediately after the system, so that you are reading yk, right? You are not reading yt, you are reading yk. But it is obvious, right? Your yk should represent yt accurately. Okay. So if you look at the transfer function, ys over us, the continuous time plant, okay, it is 1 over s plus a if it is a first order plant. We are taking first order plant for simplicity. Then if you want to calculate yt, right, because you want to figure out what sort of changes are introduced by the sampler, we want to get to yt. So yt is the Laplace inverse of 1 over s plus a times us for a given input, right? Again, if you further assume that the input is impulse, then us is 1, okay, just impulse. Then the inverse Laplace is just 1 over s plus a. And if you look at the table, Laplace table this time, right, it is e to the at, pretty obvious. So you have the impulse, just one spike, and on the output side, you will see it goes up and dies down if the system is stable, right? For all a greater than 0, over here, all a greater than or equal to 0, system is stable, right? Now, if you look at the same plant after discretization, after this sampler, okay, this YT, the same YT is not going to change, right? Because of the sampler. YT it remains unaltered. It doesn't change because of the sampler. Sampler is just a passive device. You take samples out of YT, right? How closely or how sparsely you take the sample is the issue here. So Yk after sampling is actually Yt at time equals Kt. That is simple modeling, right, of the sampler. So K is 0, 1, 2, and so on. Then it becomes e to the minus a capital T K. So the simple T is replaced by K capital T, where capital T is the sampling interval. Okay. So after this step, time is not the variable of this expression, but it is K. Okay, it is Yk, kth sample, right? And on the right hand side, e to the minus at, the whole thing is taken as a constant, e to the minus at. This is the constant. So the t goes away. Continuous time is anyway not there. Even the sampling interval, capital T, is also get concealed or wrapped up with this e to the minus at, remaining or leaving only k as only variable. So k goes from 1 to 2, 3, 4 like that. It is e to the minus 80, the whole thing as a constant times k. Okay, right. So that is one thing, and we know pretty well how to read this expression. And if you look at the Z transform table, right, if you have anything to the power k, right, anything to the power k, the Z transform is Z over Z minus that thing to the power, without k, you put it over here. This is the time domain, is the Z transform. All right. You can see the time domain e to the minus 80k. You take this k out and put the rest into this format, and that is the Z transform of that discrete time signal. There you can read the pole. This is a single pole system. Of course it is, because it is 1 OS plus A. Yeah, minus A is the pole in the continuous time. But in the discrete time, the pole, it is still single pole, and the pole location is what? E to the minus A capital T. So this is the discrete time pole. So if you draw the discrete time, the Z plane, it is somewhere over here. All right. Now, you can see it over here, the left half plane pole. After the discretization, right, system becomes a discrete system, and the pole becomes a discrete pole. And it is, if it is within the unit circle, the plant is stable. If this is stable, this is stable, right? Now, the condition for the continuous time to be stable is A greater than or equal to 0. Now here, when A is greater than or equal to 0, right, is a positive number. T is anyway positive because it is time. This is e to the minus constant. So therefore, it is less than 1. Because e to the 0 is 1. E to the negative any value is less than 1. So therefore, this point is within the unit circle. Okay. So if this is condition is satisfied, if A is on the negative half plane, e to the minus 80 will be within the unit circle. So in this slide, we have both worlds connected very nicely, the continuous time thing and the discrete time thing. What you need to understand here is that continuous time plant is not going to change because of the discretization. Okay, plant doesn't change because of the sampler or whatever. We take the reading through the sampler, and then we need to judge how accurate are the signals coming out of the sampler. Okay, how frequently we are getting the samples and so on. Here is the extension of the same theory. Continuous time system 1 OS plus A is stable for all A greater than 0, right? I think we saw that. Then the sample system has to be stable as well. Okay. The sample system cannot be unstable because of just the sampler, right? If the system is stable, because the sampler is only taking the readings. As per the corresponding discrete time system, which is Z over Z minus e to the minus AT, stability criterion is that the pole, which is e to the minus AT, stay within the unit circle. So less than or equal to 1. And then if you take the natural log of this one, this is ln1, AT should be less than or equal to 0. So of course, this is the condition for continuous time system to be stable. So if A is not positive, then the continuous time system is unstable, and the e to the minus AT will not be inside the unit circle. So both systems are unstable. Okay, right. What about a second order system? How well can we tackle the second order system? Right. Let's give it a try, because it's very important that you are competent in math here, right? So let me take this as my second order system, beta over s plus alpha square plus beta square. It's a generic second order system, right? And the sampler, capital T. So this is my continuous time part, and this is the discrete signal of the continuous response. Okay. So the characteristic equation of the continuous time plant, this one is s plus alpha whole thing square plus beta square. When you set that to 0, okay, then you get the eigenvalues. So the poles of the transfer function as -2 alpha plus or minus 4 alpha square minus 4 times alpha square plus beta square over 2. Either you know how to do that. Then once you solve this, it becomes minus alpha plus or minus j beta. So why we write the transfer function in the first place in this format is that you can clearly see what comes with S is the real part of the pole, and what comes here as positive plus beta square, the beta is the imaginary part. Okay. So even without doing any of these things, right, a conversion person could tell me alpha is a real part, beta it is a imaginary part. So the poles are alpha plus j beta, alpha minus j beta. Okay, alpha, a negative alpha rather. Okay. Now, then you put the unit impulse as the input. So US is equal to 1, and output for that one, that is unit impulse response, is the Laplace inverse of this one. So it becomes e to the minus alpha t sine beta t from the table. If you look at the table, the inverse Laplace of a function like this format is actually this. And if you look at this is the amplitude of the sinusoidal waveform, and if the amplitude is increasing, system is unstable. Okay, so alpha has to be greater than or equal to 0 alpha, because this exponent has to be negative. If you have a positive exponent of E, right, then it is growing. The system is unstable. So alpha has to be greater than 0. Of course, if you go over here, you can tell me this is minus alpha plus or minus j beta. So alpha has to be positive. That is the condition for the poles to be on the negative half plane. Okay. All right. So this is the illustration of the two poles, right? minus alpha plus j beta and minus alpha minus j beta over here. Now let's bring in the sampler, which will discretize the continuous time signal yt here. So t equals k capital T. We get the samples at every capital T, right? So then it becomes, this is the response e to the alpha t sine beta t. These t's become k capital T, right? So this is e to the alpha capital kt, k capital T rather, and sine beta k capital T. All right. So capital T is the sampling interval. Then you can see it goes into the system now, right? Capital T, which is the sampling interval, is now embedded into the plant model, right? And then K, which is the time index, becomes the only variable here, right? Some people do not understand this one. They sometimes confuse themselves. Where is the sampling interval, right? Because when you see K, K is independent integer. It goes from 0, 1, 2, 3, 4 like that, right? And you think for different sampling intervals, you need to have different waveforms, right? So where is the sampling interval? Sampling interval has been embedded into the system, to the response, to the waveform, and now you don't see it. It is inside already, okay? Right. Now, this is your discrete time signal. If you want, you can put some alpha and beta, and also sampling interval by whatever value, 10 milliseconds, say 100 milliseconds, half a second, anything, right? And then get your k to 0 to whatever value, and then you can plot it, okay, for a particular system sampled at that particular sampling interval. So we'll see different waveforms of the same plant, okay? So sampling is extremely important because it's going to be a hardwired part of the discrete time plant. Even though you have the same continuous time plant, you generate many discrete time plants because the sampling interval. Now, if this is your signal, that the discrete time signal, the Z transform of that signal, right, referring to the Z transform table, is as follows. Y is it? Is it e to the minus alpha t sine beta t? Right, this one without k, right? Over z square minus 2z e to the minus alpha t cos beta t plus e to the minus 2 alpha t. So this is coming from the table, directly from the table. If you see a sinusoidal waveform and in front of that exponential scaling like this, right? What is the Z transform of this one? The table will tell you like this. Then you immediately have your YZ. This is very much similar to the transfer function of the plant in the discrete domain. And then you get the denominator and set it to 0 and calculate your eigenvalues, discrete eigenvalues, so discrete time poles. So the poles of the characteristic equation, this one, you can directly write it, right? As follows. So you have the real part plus or minus the imaginary part, right? Once you go through this simplification, you can see it over here, e to the alpha t as the common term, e to the alpha t, e to the alpha t, e to the alpha t, the twice here, and get it out of the square root, and then out of the whole thing even, and this is cos beta t plus or minus j sine beta t. Now, cos beta t plus or minus j sine beta t is actually e to the plus or minus j beta t, right? So two plots actually, right? Two poles. One is e to the plus j beta t, the other one is e to the minus j beta t. So beta t is the angle. Is that clear? So you have the real part constant, which is e to the minus alpha t. That is the real part. Okay. And then the imaginary part is plus or minus, right? Plus j beta t or minus j beta t. J is the imaginary symbol and beta t is the angle. Okay. So remember, this is the exponential representation of the poles. It's not the algebraic format like alpha plus j beta, right? This is the exponential format. So if you take e to the alpha uh, uh, t, it is the magnitude. If you can see it over here, this is the these are the two poles, right? Pole radius is the same, and the radius is actually e to the minus alpha t, e to the minus alpha t. So if it is, as you see in the previous slides, if it is closer to over here, it's a very slow decay signal. It takes long time to decay the signal or settle the signal. But if it is closer to the origin, it quickly converge. Okay. But more than that, you can see the angle over here, right? J beta t. So beta t is the angle. So what is this angle? This is the sampling angle. Sampling angle. And you can see the t here. If you have very long t, okay, big value for t, this angle is big. So when you have a long time between samples, right? In between the signal changes, and by the time you take the next sample, the signal has undergone, right, a fairly big angle. That's why you need to make sure your t is not that long, right? It's long enough so that you're not missing any useful information of the signal. Eventually, your discrete signal, discrete version of the signal must represent closely the continuous time signal, which is the original signal. And you know that if you want to sample a signal, sinusoidal signal, right, with minimum accuracy, right, minimum, which is not anyway sufficient, right, the minimum, this angle has to be less than 180 degrees. You know that, no? 100 degrees. So if you are sampling a waveform, let's say 10 hertz waveform, 10 hertz, right? 10 hertz waveform. What is the minimum sampling frequency? Can anybody tell me? There's a sinusoidal waveform, let's say 10 hertz. So every 1 second, it goes through 10 cycles. If you want to discretize or record this waveform as a set of samples, what is the minimum frequency you should apply? We have an answer in the chat, 20 hertz. Correct. 20 hertz. So, which means every cycle, you need to get at least 2 samples because this is going upward and downward, right? You know that. If you just look at one sinusoidal waveform like that, you need to take, if you want to capture this one, you need to take one sample over here and the other one over here. Wherever it is, doesn't matter. One in the first half plane, another one in the next half plane. So therefore, per sample, sorry, per cycle, you need to have at least two samples. So which means your sampling rate has to be minimally twice the signal frequency. Okay. Now, if you think of a signal and look at this signal, it's not purely sinusoidal, right? It has a lot of sinusoidal waveforms. In that case, you pick up the highest frequency component in the signal. Okay. If it's a multi-frequency composite signal, it has 5 hertz, it has 10 hertz, it has 50 hertz, let's say. You pick up the maximum frequency, 50 hertz, and multiply by 200 hertz. And that is your minimum sampling interval. Sorry, sampling frequency. But that is not adequate. You need to go at least about 4 or 5 times of that. Right? If it is 50 hertz, your maximum signal frequency, right? Then you better sample it at, say, 400 hertz. Okay, like 8 times. Then you know there are a lot of samples you are taking here, right? Here and here and here. So many samples. Not too many, but enough samples to capture all of these variations, right? If you do that, you can keep that as a good record and do a lot of processing, right? And your results will be approximately equal to the continuous time signals. All right. Now we have a pretty good understanding about the discrete time poles, right? So if you get something like this, um, you're good. You're good in the sense you are not too close to the unit circle. Look at here. You are not too close to the unit circle. Okay, you are well within. So that is a good sign. You have the fast converging system. We prefer that. And also inside the unit circle, so the system is stable, also good. And the sampling angle is less than 45 degrees or so, right? So which means you can have how many of these angles in one cycle? Say 1, 2, 3, 4, 5, 6, 7, 8. 8 samples in one cycle, right? If you just assume this as 45, right? So that is enough samples to capture signal variation. Okay. Now, if you look at different cases here, what if alpha equals 0? Alpha means the real part in the continuous time, okay? So remember in the continuous time, we are actually coming from over here, right? Minus alpha plus or minus j beta. So these are the continuous time poles, right? Minus alpha is the real part. J beta is the imaginary part. Okay, remember like that. So these are the continuous time poles. So now, if you assume alpha to be 0, then both poles are on the imaginary axis over here. Then you know it is sustained oscillations, right? It is not decay. So in that situation, right, alpha equals 0, you have the poles over here and here. Pure imaginary poles. System is oscillating forever. And if you look at the continuous time, when alpha equals 0, what will happen to the radius? It is e to the minus 0 t. So which is 1? Then your pole is actually right on the unit circle, which means it will take infinitely long time to decay. It will not decay actually. So the response will oscillate forever. Okay, because there's this angle between samples and it will sustain forever, these oscillations. What about case 2, where alpha is 0 and so is beta? Beta is also 0. So in that case, the continuous time case, both the real and imaginary parts are 0. So your poles are right on the origin, right? And we saw that in the first semester, we call it rigid body dynamics. Okay, because there's no damping or anything. And whatever you give to the system, it will immediately be implemented, come out of the plan without any time delay or without any dynamics, right? Like a very rigid body, piece of rock. So corresponding point in the Z plane is over here. When beta is 0, the angle is 0. You know, this is the angle. When beta is 0, this one is on the real axis. And already alpha is 0, so therefore radius is 1. So it's over here, right? And this is what is called the rigid body dynamics. And you also don't like it, and you don't have that kind of systems in the real world, because real world you have dynamic systems, right? Because some sort of signal transformations happening without directly transforming from input to the output, right? So this is the case where there's no such dynamics in the system. Input goes to the output directly, right? Case 3, alpha is goes to minus infinity, way too far down in the negative direction. And you know, system is very fast, but it doesn't have enough magnitude. In that case, what will happen to the radius? Alpha is very big, then e to the alpha is very small, e to the negative alpha. So it is back in the origin. Okay. So when it is radius 0, there's no point of discussing about beta, right? There's no point in discussing beta because radius is 0. So you are over here, all right? Let's take the other case, case 4, 2 real poles. In the S plane, you have 2 poles like that, very common case, right? We have discussed this so much in the first semester. So where are the corresponding discrete time poles for this continuous time case, right? Then what you need to do is look at before and after, right? When the pole is at the origin and in the S plane, right? The rigid body dynamics, the discrete time pole is over here at 1, 0 point, okay? And you also looked at when the poles are in the negative infinity on the S plane, correspondingly the discrete poles, they appear at the origin. So it's very clear now that when you, as you move from origin to the negative infinity on the real axis, right, the discrete pole will start from 1, 0 and try to approach the origin. Comes like that. So therefore this 1 will be over here and 2 will be over here. So the overdamped, right, response, second order plan will have some something like this in the continuous time. And in discrete time, it will be like this, 2 poles on the real axis between origin and 1, 0. Okay, please remember this. This transformation is highly complicated, so that it is very difficult to visualize it. So best way going forward is that to figure out these specific cases, like pole at 0, pole at infinity, like that, or pure oscillatory poles, and figure out their corresponding positions in the Z world, okay, Z plane. And the last thing I want to show you is the constant damping ratio. You have heard of damping ratio in the first semester, right? In the S plane, it is this angle, constant angle, beta. Remember, we did that. So any pole on that axis, right, which creates the same angle, all right, we call it constant damping ratio. So these positions 1, 2, 3, 4, and so on, right? The constant damping ratio cases, right? When you transform them to the Z world, right? You can see this point here at the origin will end up being here. And all the other points will be located like this. And eventually, when you get your beta, which is the imaginary part in the continuous time case, is equal to the frequency of the waveform, omega, right? Actually, this is the Nyquist frequency, right? Then you will see, this is the limiting case, right? This is the limiting case. You will see in the discrete time, the point right on the real axis, but the negative half plane, well within the unit circle. That's okay. System is stable, but you will see this sampling angle, right, which is equal to 180 degrees. So this happens when you slow down your sampling. When you slow down your sampling, right, it's the same constant damping system, but you are taking samples very sparsely, right? And when it's over here, right, your between the angle between samples is 180 degrees, and you are right on the real axis, and you are going to create some problems. It's not a stability problem, but it is what is called inaccurate sampling problem. Inaccurate sampling problem, or aliasing. You may have heard that word, aliasing. So if you further reduce your sampling, you enter into this area, then you will see this angle is more than 180 degrees, right? Then your samples will not represent the original signal at all, right? So suppose it's a sinusoidal waveform like this, and you take your sample over here, the first sample, and after 180 degrees, right, maybe you are over here, but you don't take samples even at that point, right? Maybe you are late, you are taking sample right over here. This is the first sample over here. This is the second sample over here. And if you continue taking samples like that, having more than 180 degrees between samples, adjacent samples, if you look at your samples and try to reconstruct the waveform, you will reconstruct a very low frequency waveform. That frequency was not there in the original signal. It's a completely new frequency that you are generating looking at your samples. Okay? There was no such thing in the original signal. You create it artificially, and we give it a name, alias. It's an alias, Okay. If you use that kind of signal to drive a controller, right, you are in serious trouble. You are in serious trouble, and it will be very difficult to troubleshoot even. So therefore, it is very, very important to make sure that your discrete time signal does not cause this problem, sampling. Right? So we do the discretization to make life easy, to enjoy a lot of advantages, benefits in the discrete world. But you have to make sure your sampling is sufficiently high and you read your waveforms accurately, right, to do a good job using these samples. And there's no point of reducing the sampling rate and increasing the angle between samples, right, to a level where the samples you are taking, right, do not represent the original waveforms. Okay, in that case, you don't have any advantage at all. In fact, you will actually degrade the performance of the plant seriously. Is that clear to everybody? So what we have learned there is that there are ways to find out whether you are doing sampling accurately or in a fair manner. If you want to take so many samples, that is not good because that is not the purpose. The whole purpose of going discretization is that to reduce the bandwidth, reduce the data load. Having to deal with the continuous system is a torture, right? Because a lot of data is difficult. So reducing the waveform, the sampling frequency helps a lot. Reduce bandwidth and a lot of convenience there. But there's a limit, Nyquist limit, and you can't go below that. You can't even operate at Nyquist frequency. That is also not good. So you need to maintain your sampling at least about 4 or 5 times the sampling frequency. Okay. Now we have a little exercise to do. Take a piece of paper, right? Try to work this out. Find the discrete time pole locations of this plant. GS is equal to omega n square over square plus 2 zeta omega n plus omega n square. It's a generic second order plant, right? And we are going to discretize this plant. And you are given zeta as 0.6 and omega n as 5 radians per second. So this is a natural undamped frequency, 5 radians per second. Discrete time pole locations. Then check stability against sampling interval and check aliasing against sampling interval, right? So as I can help you get a start. Now the whole thing depends on the sampling interval. So initially you can have some sampling interval, capital T, and then figure out your pole locations and then figure out what are the limits for capital T, for stability and for aliasing. Okay, right. Please take a few minutes, say, yeah, 5 to 8 minutes to fix that problem. All right. You may check your answers. So it's a simple sum. So you have the transfer function, which is this one, generic second order plant, where the natural undamped frequency and the damping ratio are both given as 5 and 0.6, right? You just write the transfer function and substitute 5 here and 0.6 over here, right? So this is your transfer function. That is the first part. And then pick it up from there, the denominator polynomial, and set it to 0 to get the characteristic equation, right? And then calculate the eigenvalues of that quadratic function, and you get this one there. So it is basically -3 plus or minus J4, right? There you can see the natural undamped frequency, and this is the damping ratio. Now, if you look at sampling, this 4 is critically important. This omega d is critically important. All right. Now, if you look at this 5, what is that 5? Where is that? This one, omega n. So this is the undamped frequency, natural undamped frequency. It's not something that you see in your response, right, which is coming out of the plant. What you see is the damped response after, because there's damping, 0.6 damping is there. So therefore, you don't see omega n in the output or response. What you see is this 4 radians per second. Okay. Now, the problem is very clear. You have a varying signal, sinusoidal waveform, right? With 4 radians per second angular speed, right? And for the moment, you can forget about the damping, the decay. This -3 decay, of course, it decays the amplitude of the waveform, but that's a separate issue. So you are dealing with a 4 radians per second signal, and you have to tell me what is the minimum sampling rate for this waveform. Can anybody guess? You are dealing with 4 radians per second signal. So you have to sample it at least at 8 radians per second. If you work with radians per second, radian frequency, it's 8 minimum, but preferably maybe more than 30 radians per second. You have to get enough samples, right? Okay, that part is clear. Now, the 2 poles, right, in the continuous time are like this. Now, let's say we are discretizing the whole thing. We are going to bring in a discrete time controller, and we are going to put a sampler here and all of these things. So you need to convert this continuous time plan into discrete time. And when you do that, as we have gone through the theory, right, you can directly write it like this: e to the -3 plus or minus J4 times capital D. So this is the is a transform definition over Laplace. Okay, there's no need to go back to the first principle and derive it again. Have the continuous time poles and then put it into this format, and these are your discrete time poles. Now you have to check whether they are within the unit circle, and then if the case they are stable, you have a stable system, and whether the sampling is enough. Check the beta t, which is the sampling angle. All of these things you can actually verify. Okay, so please study or learn the process, right? So then you pick up the first part here, e to the -3t. This is the check the magnitude. So this is the radius of the poles, right? 2 poles, and you can check whether this is closer to the unit circle or closer to the origin. And you can see it depends on capital T. Okay. So if you have a very small capital T, what will happen? Very small capital T. This will be minus very small value. So you are getting closer to the origin, okay, to the unit circle. But if T is very, very big, so you have a very big negative value, then whole thing becomes very close to 0. So it's a fast decay system. Okay, but it's a bit confusing here because when you have t very small, right, your samples are very close to each other. Okay, but when you have very large t, your samples are far apart. So time wise, maybe it's the same time, but you have so many samples in that time duration, right? If you have very small t versus you have big t, right? So therefore, when I say fast and small, I'm actually referring to the number of samples, not the absolute time. Okay, right. And the other one is the imaginary part here coming from this J4. It is basically the angle 40. So this angle is actually 40. So put a value for t and multiply by 4, and that is the angle in radians. Okay, angle in radians between samples. So if this angle is closer to 180 degrees, you are not good. If the angle is like 30 degree, 40 degree, right, maybe you're okay. So this is how we judge, right, whether our sampling is good enough, right? So you can write down the two discrete poles in this format also. E to the minus 3, you take the real part, right, which is the radius of the pole out, and then this angle part, right, you can write it like cos plus or minus j sine. Okay, this is a trigonometric format or algebraic cosine and sine combination, right, with the unit magnitude, and actual magnitude is over here. So you can easily figure out again omega TP is 2 pi, right? This is the omega, and then TP is 1.57, or if you want to have the frequency in hertz, it's 0.637, like that. You can read all these things from the poles themselves and evaluate the performance, right? So put some values for t and plot the two poles as a homework, right? For small values of t, for big values of t, and judge on the pole radius and pole angle, and therefore what is the possibility of getting into aliasing problem, right? When you have this 4 capital T is equal to exactly 180 degrees, that is pi by uh, equal to pi, right? So then this is the limiting condition for aliasing, and you can calculate your T, right? So sampling frequency, sampling interval, all these things can be calculated over here. Any questions about this, please?
So there the TP is taken as what, sir? TP
It is the period.
period.
Yeah.
Okay.
So if you do the sampling, right, and you pedal back, so that, yeah, over here, or maybe one, yeah. So what is very important is this term here, beta t. In our case here, we have beta, oops, we have beta equals 4, I think, right? We have beta equals 4. That is the damped frequency. So so this is the actual angle between samples, actual angle between samples. When this reaches 180 degrees, right, you are at the verge of aliasing, right? That is actually the Nyquist rate. And if you further delay at that time, if you calculate your t, right, for 180 degrees, and then if you take the invert, you get the reciprocal of t, you get the sampling frequency. You know that, no? Frequency is equal to 1 over t. And that is the Nyquist rate. That is the Nyquist rate. If you further delay, right, if you further increase t, the frequency will further reduce and you are below the Nyquist rate. So there's nothing called below the Nyquist rate because system is already generating aliasing frequencies. So you can go down and down and down in frequency, and you can go up and up and up in terms of t, right? When you increase t, right, you are coming like that, and you are reducing your sampling frequency. And when the t increases to a certain value, right, when the sampling frequency further reduces to this value, when the pole is over here, that is the Nyquist frequency. And if you further increase the time between samples, you are maybe over here and you are below the Nyquist frequency. So then it's not good. System will malfunction basically. If you close the loop through a sampler which is operating below sampling, below Nyquist rather, you're not going to create any meaningful action in the control. Okay.
Right, sir.
So this is another illustration of the same thing. In terms of stability, e to the minus 3t is the radius, right, of the pole. And if it is less than 1, system is stable, right? The waveform is stable. So because this is e to the minus 3t, t is of course a positive number. So therefore this is anyway less than 1. So signal is stable. Okay. So this is very interesting. Sometimes you think the stability is the only problem. No, stability is just one problem, a major problem. And aliasing is another one. Aliasing is another one. You can have any t here and say that for any t, this is stable, right? That is true, but it doesn't mean that you can have a good controller. System is stable, fine. But can you have a good controller? No. To have a good controller, there are more restrictions for t. If you just look at the stability, there is no restriction for t whatsoever. For any t, system is stable, right? So that is to say that the signal over here is stable. But that is not what we need in terms of control, right? In terms of control, you need to have the sampler design and then get the Y and a feedback and then generate some control signal, right? So to do that, there are more restrictions on T, right? The number one restriction is sampling, aliasing. So you have to look at the aliasing and then adjust a capital T accordingly. So stable GS has stable ZS, right? Under any T. So that is one thing. However, slow sampling may cause aliasing in the feedback loop, which will deteriorate the response. Now, what you see over here is a sampling at 4 Hertz. That is about quarter second, right? And the two poles are like that. This is arbitrarily set sampling, 0.25. So when T is 0.25, sampling is at 4 Hertz. Sampling is at 4 Hertz. Right? Then this is your waveform. Sampling at 4 Hertz, maybe roughly something like that. Right? Roughly something like that. So the samples are not actually enough, but you can see you are capturing the waveform. That's all right. But if you further reduce this frequency to maybe 2 hertz, then you are taking, maybe you are missing this one, right? And you are also missing this one. So you have this sample and another one over here, right? Then you have trouble plotting the graph, right? That is the problem. You have no idea about the actual shape of the curve looking at the samples. So generally speaking, it is better to have the sampling fixed at least 4 or 5 times the Nyquist rate. Okay, don't go any below that threshold. All right, any further questions, please?